Dear colleagues, we continue our work. And the first presentation of this session is the first presentation is in this session is enhancing mobile manipulation in home environments, a case study from the Neuro IPS 2023 Home Robot Challenge. Presenter
Владислав.
What's the name?
Гуменний.
Vladislav Gumeni.
Okay, thank you. So, as I was introduced, I will introduce also my research partners, Volodymyr Kuzma and Ruslan Toktsey. The research was done in collaboration with them. Let's get to our quick agenda. We will start with quick overview of embodied AI sphere. After that, I will talk about challenge in which we participated, and then I will talk about our solution. So let's start. Embodied AI. Well, you can see that the term consists of two components, embodied and artificial intelligence. Embodied is a part of a robot, a body which is controlled by some artificial intelligence that does all movements. You have seen such dog-like robots, vacuum cleaners, some manipulators, or even humanoid robots. All of them, they are embodied AI agents that are acting in the real environment. And with each day, we get more and more robots around us. And to make them very useful for us in our everyday life, they have to be intelligent, as most of the challenges in our real life have to we have to create creative solution. And for that, our agents have to be intelligent. But what is intelligence in terms of embodied AI? Well, at that year conference, CVPR 2024, there was the next 5 components that combine a very intelligent robot. Well, the first one is C. Agent has to have visual perception of everything that happens around it. The next one is talk. It has to give audio output for a person to so the person understands what it does and what it had done. Also, listen. The robot has to understand what is happening around it in terms of audio, and also it has to understand what person talks to them. Act. If the agent doesn't act in the environment, then it is probably not very useful agent. And also the agent has to reason. Is in fact, if it has some goal, it has to create some long-term plan for that goal to be successful. Let's get to some example. We will start with pick and place. It is very basic example of in terms of embodied AI, when we have to take some object and place it in desired position. It is combination of C and ACT from the previous slide. And in fact, pick and place is very simple, but it is very basic for the whole embodied AI industry. And it is important to solve such named enclosed environments, as we can see on the slide. But how to teach the robot do what it has to do? Well, we have two main ways to do that. The first one is manual write algorithm for that. In that way, we would explicitly state all the logic, and if the robot sees something, then we do the next thing. That is a lot of if-else statements that we have to satisfy. The next way is to let robot learn by itself, and that is the way of neural networks. And to be particular, that is reinforcement learning. That is the way when the robot does a lot of trials and errors to understand what the action is good and what the action isn't that good. But both of those methods, they have a lot of cons. And the main are, for the first one, is we can predict all scenarios in our world because it is very big and complex. And for second, it is very hard to configure such reinforcement learning training. So we can't be sure that it was ideal. So with all of that information, let's get to our challenge. Its full name is Open Vocabulary Mobile Manipulation. We will understand each of those words a bit later. But in fact, what is OVMM task? That is pick and place with an asterisk. We have the next goal. Move object A from receptacle B to receptacle C. Receptacle in that context is just a surface where we can place some object. And unlike the previous example, we have a very big environment in which we can move. So we can see that there is a mobile platform that moves around the house, and it has to do the task. There are 4 subtasks. The first one is to locate the object. The second one is to pick it up. The third one is to find the goal receptacle. And after that, we have to place it. So that 4 subtasks, they form the whole big pick and place task. And all of that is trained and assessed in simulation, but final evaluation of the challenge is done in reality. So say hello to Hello Robot Stretch. That is a robot that is used both in simulation and real world. In simulation, it is just a model of that robot, but very precise. It has mobile base to move around the house. It has 3 degrees of freedom manipulator wrist. And all of that combined, we get 7 degrees of freedom robot that is very lightweight and cheap, of course, relatively to its competitors. And it is perfect for indication and personal use. And such a base, it is very good for research because it is very easy to understand how to move it, how to control it, and its learning curve is very good. But what is importance of such OVM task at the global scale? Well, we can say about injured people, for example, during the war in Ukraine, or some people with disabilities. Let's look at the case of Henry Evans. In 2010, he lost ability to move, so he couldn't move around by himself for a long time. But he collaborated with Georgia Tech University and Hello Robot, and they created that robot Stretch for him, with which he could go around the house with that robot, help himself, and interact with, for example, his grandchildren. So we have 2 parts. The first one is reality, and the second one is simulation. Our final goal is our success in the reality, but there's a lot of problems. Reality doesn't have simplifications, and it is very hard to make experiments on scale, as we have limited number of robots. In fact, during our challenge, we didn't have any. And it is very hard to set up them because each time the person has to do that by himself. But in simulation, we have a very different scenario. It is a simplified version of reality, and it allows us to create a lot of experiments on the big scale simultaneously. So with all of those simulations, we can train our robot to become very good at such a simplified version of that task. And after that, we can mitigate that knowledge from simplified version to the reality. And here are the main challenges of the OVMM task. Well, the first one is visual perception and open vocabulary challenge setting. Open vocabulary means that our objects with which we have to interact, they're not fixed. So it is not closed set of objects. It can be any object. It can be marker. It can be some ways. It can be anything that will be prompted to you. So you have to be ready for that. Also, that is navigation. You don't know about environment before the start of the episode. So we have to explore it, and you have to find and memorize everything that is around the room. And also manipulation. It is very hard to work with one point of view and the arm. So sometimes we have interfering movements of arm that doesn't allow us to see the objects that we want to grasp. And here's a little analysis of OVMM paper. I don't want you to look at the middle columns, but on the most left and the rightest. We have on the left different perceptions. Perception is how we understand RGB image that is given to us. So we have RGB image, and we have to understand what objects are on it. We create, you can see here, semantic segmentation, and we can understand what object is where. Ground truth perception is when we understand ideally with pixel accuracy what is what object, and DATIC is the custom model that does it because it was trained to do that. And we can see that when we go from ideal perception to some custom, we can see that our overall success rate, it falls tenfold and even more. So we can see that perception, it is very influential over the course of the whole episode. And it is obvious because it is used during every subtask of our challenge. So it was one of our main goals to improve perception. And also we analyzed different skills. Well, we have seen that place object has the lowest relative success, and also it is one of the most important skills because it is the last one. If we want to succeed in the whole challenge, then we have to place the object. If we get to place section but don't place the object, then we failed. So it is our bottleneck that we have to focus on. With all of that, I will go to our solution, and here main key improvements ideas. The first one is our perception. It is a combination of two models. The first one is open vocabulary, which understands almost any object and can find it. And the second one is fine-tuned detection model that is fine-tuned only for household objects, because our challenge is done in household environment. Also, we improved our place model. We enhanced its behavior and its starting position. So it is feasible to finish a place successfully. Here's our agent architecture. When below you can see its high-level heuristic, that is how it behaves from the high level. At first, it starts navigating to object. It tries to gaze at object if it is close to it. And if it is successful, then we go to navigation to receptacle and to the place. If it wasn't receptacle, then we start from the beginning. But let's look at those yellow blocks more. We can see that, in fact, those are reinforcement learning agents that were trained to do some task. We can see that on the input, we have observations, which are RGB images, semantic segmentations, and depth view. And also we have other sensor measurements like position of our arm or position of the robot in the environment. So it is X and Y coordinate. We pass through our RGB images through convolutional neural networks and our other sensor measurements through fully connected layers and concatenate them. After that, we pass them through recurrent neural network that allows us to know what we are doing right now and what we have done previously. So we have a bit of memory of our actions. Also, here's what is we done with perception. There are two branches of it. The below one is DETIC, that is open vocabulary model that can segment objects without pre-training. And this upper one is our custom model that combines model YOLO that detects the objects and gives us those boxes around them, bounded boxes. And after that, with use of them, we segment the objects. After that, what we have two different segmentations, and we use confidence scores of each model to layer them. If someone's score is higher, then it is layered upper somewhere, something, and in other ways, it does the same. So, in fact, after that, we get our final semantic segmentation that we used for the challenge. And how it is its success in the real world, as we didn't have the robot to test it, so we just tested the perception because it was the only thing that we could test in the reality. Also, how we improved place, as well as at first we recorded behavior of the robot, and you can see on such example that robot just puts its arm into its vision, and after that it is not possible to solve the task because you just can't see anything. So from that we had some conclusions, and also we analyzed different training metric. With all of that, we had the next reward enhancements. We wanted the agent to have direct vision on the target, so we created a reward for that. And also we penalized blocking the camera with manipulator, so there were no such stations as on the left. And also we penalized stopping the agent farther than 1 meter from the receptacle, because if it was such far from the receptacle, then the place action was not feasible at all. So we wanted to make it feasible, at least in all situations. That is different performance comparison of our different settings. At the end, we got 5.2 overall success rate, and that was done on our training, on our set. And that is our results on the sets of organizers. We got only 2.4% of overall success, and the first team got 10.8% of the overall success. Well, let's look also at competitors' approaches and why the first team had almost 4 times bigger success than we. Well, the first team, they focused on finding the weaknesses and improving them. And because they found such many weaknesses, their success didn't improve only by 1% each time. It was exponential growth as each such weakness, it influenced the next weakness. And because of that, the whole success rate fell down. So they improved a lot of parts, which led them to increase their success in exponential behavior. And what we learned from that is a heuristic approach, which our competitors used. It was more effective because you could easily, how much? Okay. So it was more effective in early stage because they could easily change the behavior. Also, it improved high-level planning. And our approach, reinforcement learning approach, it enabled agent to complete complex behaviors, but sometimes it required precise reward engineering, which was not always feasible. Also, there are other possible areas for improvements. Well, the first one was our perception training dataset. We have seen that not all objects were used to train them, especially receptacles. We suppose that with better dataset, we could have much better results with everything. Also, our high-level policy and word representation. High-level policy is how each skill is started. And we suppose that with much better improvements, like retrying some skills or different order of them, we could have better success. And also word representation. If you could memorize our environment, it could manage us not to be dependent on recurrent neural network that could forget things. And we could be sure that our behavior would be very predictable. And also object tracking. When we did our segmentation, we relied only on one frame, but we also had previous frames because we were moving. So what we could do is to use not just segmentation, but tracking of the objects. And we suppose that all of that would improve our consistency, and it would, in fact, have better consistency over the whole episode. So that's all from me. Do you have any questions?
Thank you for the talk once again. The main angle of the recording. I have a couple of questions. There's one important component that is missing from the whole pipeline. This component is, well, you mentioned reinforcement learning, the low-leveler control policy. You mentioned the vision part. You even talked a lot about the reward engineering. What about the agent actually deciding what to do, like motion planning? Have you thought about that in any way?
All actions are done with use of reinforcement learning. So each of place, gaze, navigation, final action is here, AT. So it is done with use of reinforcement learning, which was trained. So it was trained to perform the best action in each scenario. in navigation, it could only navigate to the object, and in different in place and case, it could control its navigation more precisely. So it wasn't a discrete step like 0.3 meters. It was more precise by 0.1 meters in each direction. And also it could control its arm. So those actions, they were learned by those reinforcement learning checkpoints.
Yeah, but this is still not, this does not completely answer my question. Planning is completely separate from reinforcement learning. Well, you have the latent space from after the RNN there, which is not like feasibly flexible enough to learn the representations within the actual inside the room or inside like a kitchen or something. This is just rigid memorizing, like pretty much overfitting towards the distribution of sample space. That's just okay. Anyway, thank you. I have another question, if you don't mind. You mentioned like you did a lot of things with the computer vision part. What about the reinforcement learning? What's the algorithm at least under the hood? Because I'm not familiar with the paper. I'm just curious. What's the algo?
Yeah, about previous, yeah, we didn't use word representation, and we thought that it was our flow of our solution. And about reinforcement learning, we used DDPPO, that is distributed decentralized
Proximal policy.
Optimization, yeah. And what we did, as we had only limited computational power, so we focused on improving the place checkpoint. So we had it, and
okay. And
yeah,
this is
so we found the better reward, and we trying to fine tune the whole checkpoint to make better predictions and to make better place movements.
And this competition is from 2024, this year's.
That is from the
last year.
The end from 2023.
Okay, I see. And last question quickly. You mentioned on the slides, you didn't talk through it, but the HSSD data set. Have you considered any other data sets like Habitat or something just to supplement your model, maybe make it see more scenes, more diversity or something like that?
In fact, we tried even to create our custom data set, but in fact, we didn't have a lot of success with that. So yeah, we tried to do that, but the best improvement in success we had only with HSSD.
Okay, thank you very much.
Yeah. Any question?
Thank you, guys. Thank you for your work. And I'm a bit confused and interested. How many different models did you train here? Like separate for navigation and separate for pick and place, or one for all? Thank you.
So in fact, we had 4 different models. The 2 of those, they had navigation to object and navigation to receptacle. They were similar, but in fact, they were trained separately because the final goal, it was very different. In the first one, we had to navigate to object and receptacle. So we had to find both of those objects that coincide on the same receptacle. For the second one, we had to have only receptacle. So it was a bit easier, and we had to only be close enough to it. And in terms of pick and place, they were similar, but they were trained differently because the final goal was very different.
So architectures were similar, but the way of training is different. It's interesting thing. And the last question about maybe some auxiliary losses techniques. How you helped them learn?
Can you please?
Did you use some auxiliary losses? Maybe auxiliary tasks that helped?
I can't say.
So just straightforward. Okay.
Yeah.
So the end of episode. Thank you.
Questions? Thank you. The next presentation is is an approach for detecting Alzheimer's disease using deep learning techniques. Presenter.
Yeah, hi everyone. Can you guys hear me?
Presenter Amal El Arid. Okay.
Yeah, hi. Look, first of all, I would like to thank you for this great opportunity. Second, I would like to apologize, Amal, due to the situation in Beirut, her internet, there's no internet currently, so she couldn't attend. I'm Dr. Muhammad Nasruddin from the University of Wollongong in Dubai. I'm one of the co-authors. I've been notified that I have to deliver on her behalf today because of the situation happening currently. I will share the file and I start. Is it clear? Can you all see the file? Is my voice clear?
Yeah, very good.
Okay. So today I'll be presenting our research paper entitled An Approach for Detecting Alzheimer's Disease Using Deep Learning Techniques. So during today's presentation, I will cover part of the introductions, part of the current existing techniques, research objective, literature review, related work, methodology, experimental result or a simulation result, and a discussion, and I end it with the conclusions. Before I start the paper, I would like to introduce the Alzheimer. The Alzheimer, it's one of the unfortunate diseases that cannot be well treated depending on its stage. So what will happen when it comes to Alzheimer diseases? We have progressive brain disorder that cannot be treated, develop slowly and gradually, worsen over the several years, marked by the first signs of mild memory loss and cognitive difficulties, common form of dementia among other adults, depending on the case conditions. Now, for us, we as a scientist, we're not a medical scientist, as a scientist from an engineering and computer science point of view, we need to understand what caused this. So there's a damage of the brain decades before the symptoms appear. So there is a certain damage. Difficulty to diagnose. This damage to the brain, if I go to MRI and I go under normal condition, it's a very difficult. That's why it is possible to use the advanced technology. One of them is deep learning or machine learning or artificial intelligence, which we're going to discuss during this paper is a deep learning. Now, what are the main challenges? The main challenging is when you go to a clinical, to do the diagnostics are not 100% accurate without the aid of an advanced software. The clinical diagnosis need a long time to be completed. So you need assessments. And this time, it's not on the patient favor. The clinical diagnoses are very expensive currently. So we're helping part of also the research that we're going to conduct. We're going to continue conducting. This will reduce the cost on the patient. Now, the main aim of this study is early detection of the disease, and we use an automated detection system. So there is a currently numerous approach or numerous system when it comes to detections. I am not going to discuss all of them because I want to keep the discussion when it comes to the result. So we have the clinical examinations, we have the MRI, we have the positron emission tomography, PET scan, we have the artificial intelligence, machine learning, and deep learning. Now, this is where we are interested in our research. So machine learning uses numerical databases with specific feature selections. The deep learning used for database with image with automatic feature selections. The research objective is that our research objective will be a strategy for Alzheimer's disease detection using deep learning and image processing technique in its different stages. If it's Alzheimer's disease, mild cognitive, or severe mild cognitive. We need to be able to address all these stages. Now, provide the deep learning technique used in this research with a clear choice explanation. So this we will see when we go to the tables, you will see this in details. Evaluate the efficiency and precision of the deep learning technique implemented in this research. So these are the three main objectives of this paper. Now, when it comes to literature review, there are numerous techniques. Each techniques will have a condition of diagnosis. So if you go ahead through the paper, you will see that we use multitask learning approach, gradient boost artificial neural network, deep learning algorithm. All this is being discussed into the paper, and each one of them has a diagnosis conditions for it to give an optimum results. The methodology that's being used in this, conceptual framework is number one, collecting data. We try to collect data as much as possible from different countries, from different organizations that have access to this image for this type of diseases. Stage number one, we have to go into a pre-processing stages, which is labeling the data. We need to make sure which category we want to put the data under. Remove any noise, any unwanted features in this data. We need to resize it. So is it 2D? You want to take it to 1D, for example? You will see this. Converting the color, rescaling, reshaping the image, handling the image. After all this, we will go into the splitting data. And when we go to splitting data, we go into three different algorithm or section of the learning CNN techniques that we're going to follow. We will use the DenseNet, we use Inception V3, and we use the ResNet 50. And based on this one, we will have a different evaluation under each one of them. So the database that we used has 1,308 images divided into 5 instant diseases. So out of this 1,308 images, we had 13.1% of them are to Alzheimer's diseases. We have 45.2% of this 1,308 images are cognitive normal, CN. We have 18.4% for early mild cognitive impairment. And we have 17.8% for the MCI and 5.5% of LMCI, which is late mild cognitive impairments. So this set of data we're going to use into our methodology. Now, let me explain every step in this methodology. So now, the 3 image processing methodology, the IPM. Number one is we discussed the filtering to eliminate noise from the image by using an average filter. Now, stage number 2 is resizing to ensure all images have identical dimension before applying them into the deep learning model that we want to propose. Then converting the grayscale to grayscale. So all the colored one will be goes into grayscale, black and white, to ensure all images are in grayscale before apply the deep learning. So these are the 3 steps that we followed before we go into the assessment. Now, when it comes to rescaling image to value to 0 to 1, we scale the image, converting the image to 1-dimensional array using the reshaping function of the program, and now handling unbalanced data set using SMOTI, symmetrical minority overshaping technique. It's a method that will be used for oversampling minority classes without overfitting by creating new artificial example in feature space. What happened then after this, we split the data into, we have the 80% of the image will go into the trained subset, and we have the 20% image goes into the testing subset. So it's very important for the trained subset, because you will see when we run the model, the difference in the outputs. So the three model of the CNN techniques that use for the deep learning are the DenseNet, which is feed forward the CNN known as a densely connected convolution network. And then we have the Inception v3, which is the architect belonging to the Inception family. And then we have the ResNet 50, which is an architect that adheres to two fundamental design principles. These are the three that we test our set. And remember, what we did, we gave him a set that has a percentage of Alzheimer, percentage of cognitive, normal of the CN, percentage of the EMCI, percentage of the MCI or the LMCI. And then 80% of this went into the training subset and 20% went into the testing subset. Now, when it comes to this element, after we did all these inceptions, we went into several metrics, including we got the confusion metrics, the CM. We discussed, I guess, the accuracy, precisions, recall, and the F1 score. This is very important for us to focus on the accuracy of our system, because if our system is not accurate, we're going to have a major problem. We're going to have a major problem in making this reality. So we need to make sure that it has a accuracy and acceptable accuracy. That's number one. Number two is we need to be a precision, because at the beginning of my presentation, I mentioned that the current diagnostic system, if I go to the doctor, is going to take sometimes, it's not accurate, it's going to cost money. So I need to make sure it's accurate, precision, and fast. That's why it's important for us to make sure that these are implemented within the actual software. Now, so what we've done is we went into the evaluating stage after we ran the module, and we checked the under predicted and under actual. So if I go ahead and I say it's a TP1, what does it mean for me? It's mean that it's a high accuracy when I went into Alzheimer's diseases. So I picked it up if it's Alzheimer's diseases. If it's cognitive, and then I picked it up, it's not, it's deviating from the accuracy that I needed. So it's very important for me to know the evaluating performance, which is between accuracy, precisions, and these are the equations that govern our module when it comes to evaluating performance. Now, we put all this image into the system. What did we find? The DenseNet model, what did it give me? It gave me 73% on Alzheimer's diseases. As you can see, there is an error. It gave 49%, 65%, 84%, 69%. So I still have one that I did not pick up correct. Why? Because I need to pick up this ones, the TP. I don't want to pick up any of this because this is not what I'm aiming for. I want to try to get, if possible, to 100%. This is for the DenseNet model. We went and we did the Inception model. So as you can see, the DenseNet model gave us a higher result when it comes to Alzheimer's diseases, because it gave us 73, this is a 66. However, if I look at the EMCI, it gave us the actual prediction for the inception V3 model. It's higher. And then when I went to the ResNet 50, it gave us similar, very high to when it comes to the EMCI. And for the AD, as you can see, 76, which is better than the previous model. So what can we say from this perspective? That it is possible to have an acceptable accuracy. Of course, it's not as we hope for. We hope that this model can now be trained to go to beyond these percentages. But where we can do this, to discuss this result furthermore after we saw all this result under the 3 different model, we have, as you can see, what we did is we did a Matthew correlation coefficients to help to summarize the confusion matrix or an error matrix. So we use the following equations to physically gives me for the dense net, it's a 0.71, for the inception 0.67, and for the ResNet 50 is 0.79. If I go into here and I want to check against accuracy and precisions. These 2 elements, as you can see, I have an accuracy of the AD of 93%. I have it for MCI as a 97%. Okay, and the dense net. When I go to inceptions, I have 90%. When I go to ResNet, I have a 95.03% based on actual and predictions. So based on the following, I can go to the precision, and also I can see the precision of the ResNet is 88.3, and it's the highest one if I look at it from this perspective. When I go to comparison, I want to compare what other people study referenced. We have the reference, we referenced it again, Mahmoud et al. Paper, which is done in 2023. They did a random forest, supervised ML. They did k-nearest neighbor. They did support vector machine, convolution neural network, artificial neural network, and the highest accuracy that they got 75% and 79% when it comes to deep learning. Now, the current study, we use the 3 module, the densenet, the inception, and the ResNet, and we use the convolutional neural network, and the result came above 80% in high accuracy. Based on the following, please allow me to conclude that the AD align the diminished patient daily activities. It's a very, unfortunately, it's a very serious diseases that impact the human life, that impact the human performance, their loved one. Early detections in PIDS is at its advanced and will assist patient in sustain a regular lifestyle. So before the tissue damage, if we can detect it at a very early stage. And deep learning demonstrated an exceptional performance in diverse domain. The AD diagnosed use 3 different type of deep learning technique. The densenet, the inception, and the ResNet. The efficiency in accurately identifying the AD through its 5 categories, as you can see, gave a promising result as a first attempt in this type of work. And for now, I conclude my presentations. Thank you for listening. I cannot hear. If anyone's asking question, I cannot hear.
Question, please.
Yes.
Please.
Yes, I can hear you now.
Thank you. Please tell me how you market up the photo samples.
What do you mean by how do I mark the photo sample? I enter in the photo sample. I've already got the photo sample from a resources. By the way, please allow me to say that after this research, we obtain almost 6 terabyte worth of data that we want to expand this research based on the image that we got. So I didn't get your question properly, but if you mean when we get the image, we take it into the software and we will make sure we go through all the pre-process stages, which is eliminate any noise available inside it, resize it, reshape it, make it gray, and it goes through the normal process.
Thank you. And second question. The CRM method showed higher accuracy than the deep learning method. Why?
Look, remember, this is the first stage of our research. The next one is we're getting now we got 1,308 image, and we did this. Maybe tomorrow we're getting, like I said to you, we just gain access to almost 6 terabyte worth of data regarding the Alzheimer's diseases, all this image. So maybe now when we go into a bigger scale, we can find if it's really true that deep learning CNN can give us a higher than the machine learning, the supervised machine learning, or any of them, or it's need to be maybe tweaked a little bit to work. So at this stage, the result shows based on this 1,308 image, which is very low number. It's not a large number when it comes to advanced, deep learning approach or machine learning. So why I need to answer it after we do all the other testing as well, all the other modeling simulation, and see if it's gonna remain high accuracy.
Any questions?
Good evening. I want to ask you about your data set. Is it right that you have only 1,300 pictures in your data set?
It's a very good question. I just was talking to our colleague now. That was accessible to us at the stage where we started the research. Now, after we communicated with the numerous entities.
No. I asked you about your data set that was used during the learning.
Yes, this data set that I used during the learning, we used 1,308.
And according to these persons, I think that some classes have only 50 pictures. Is it right?
Say again, the classes that I have, some of them have 13%.
5%.
Yes, some of them have about 13%, some of them 5.5%. That's correct. Yes.
Plus 5%.
Yes.
Do you think that it's a good data set to measure something?
Well, in regard to the LMCI, the data set need to be revised again, and like I said, in the next stage, we are going to test our software based on at least 20 or 30 times more images per sector.
Yes, of course. And I think that your numbers in the end sometimes correlated with the data set size.
That's correct. Yes.
Thank you.
Point taken. Very good point. Thank you. Very good point. Point taken. And we discussed this with my colleagues. But unfortunately, sometimes we have a limited access to data. We have to stick to what we have and, try to build on it. But a very good question. Thank you. Thank you for pointing this out.
Thank you. Questions? No. Thank you.
Thank you. Thank you. Thank you for having us. Thank you.
Our last presentation for this session is usage of cognitive network for cyber attack detection and prevention. Presenter Alexander Letichevsky. Please start.
Hello, everybody. So I am Alexander Letichevsky, Chief of Department of Glushkov Institute of Cybernetics of Ukrainian Academy of Science. And I'm going to talk about our experiments and our technology using the cognitive networks, the combination of algebraic approach and the AI methods. So, sorry. So I'm going to tell about research accordingly to the following plan. First, it's some background about our algebraic approach, overview, some theoretical and system. I'm going to talk about the system of vulnerability detection. The next, I present our experiment for intrusion detection system with usage AI, and I'll talk about the neurosymbolic approach, where we consider the synergy of algebraic approach and in the intrusion detection system that contain the algebraic and AI component. It was done for elimination of disadvantages of the both approach and usage in the industry. So the next is some theoretical background. So we resolve different tasks that require formal models. So the corresponding specification language and corresponding formalization technique shall be developed. The new paradigm of insertion modeling was used, and behavior algebra for formalization of different processes and environments. So the theory of agents and environment is the basics of the insertion modeling. It began with the work of the general theory of interaction by Professor Letichevsky Senior and the British mathematician David Hilbert from the City University of London, and was an attempt to present the theory of interaction as the interaction of agents and environments. Agent is the entity that has a type defined by the set of its attributes. It has a behavior that is determined by the set of its possible actions. An agent can be inserted in the environment, interact with other agents, and the environment can allow or forbid him to perform the actions. An agent can be an environment for other agents, just as environment can be an agent in an environment or on the higher level of abstraction. All this performed with the help of the insertion function, the property of which are considered in this theory. For example, a computer can be an environment for operating system environment for programs, agents, program agents, environment for classes, and so on, as far as we can allow. Also, we have an example from the modeling in biology, as model of cells can be environment for its organelles, and so on, up to the elementary particle that can also be agents. So we create model and specify interaction and behavior algebra. Behavior of the agents were represented with usage of the behavior algebra. An agent has a behavior that is determined by the sequence of its actions. The algebra behavior is a two-sort algebra over the set of behaviors and the set of actions. Two operations are defined in the algebra behaviors. It's a prefixing. It determines the separation of the first action of behavior. Non-deterministic choice of behavior sets the alternative behavior. Terminal constant appear in the algebra behaviors: successful termination, non-deterministic behavior, and deadlock. So Parallel and sequential composition of behavior were an extension of the operations of the algebra of behavior. We define an expression of algebra that creating using these operations. We define a behavioral equation as the equality in which the identifier of the behavior is on the left and the expression of the algebra of behavior is on the right. Using this algebra, we can describe, for example, behavior of a program of its control flow, represent cycle, alternatives, and it will be a system of equation within the algebra behavior. This slide shows an example of behavior algebra. So comparing this with well-known process algebra as Milner CCS, we can state that behavior algebra is very similar, but it's much more generalized. Milner concentrated on the semantic of interaction and synchronization of processes, semaphores, and other property of message parsing. Here we have abstracted from the semantic of the edge interaction for a broader coverage of subject domain. We set with the p-calculus and Cordelli-Mobile ambient algebra. So actions in the scope of behavioral algebra. An agent can have attributes and it defines the type of agents. Insertion modeling is generic, so you can use any type that allowed by algebraic language and can be reduced to the simple type like integer, boolean, list, etc. Agent can perform actions. The agent actions has a precondition and postcondition. The precondition is a predicate that includes expression of the attributes of different data type. A postcondition is the operation that changes the attribute and may contain a predicate that establishes a new relationship between attributes. Algebraic modeling, this is the main method. We create in the scope of behavioral equations and specify the sequences of actions of agents. We can define some initial constraints and unfolding behavior equation. With performing of action, we can get the states of agents. Initial formula and formulas of pre and post condition contain constants and arbitrary variables. So implementation of the action, it's not a calculation, but symbolic transformation of formula. The state of agent is a sum formula over agent attributes. Unfolding behavior equation, like in writing rule technique, we can get the different scenario of trace or traces. And this procedure is algebraic modeling. Algebraic modeling is basic of formal methods, and the easiest methods is to define the reachability of some property. It's a forward algebraic modeling, but we have another kind of modeling, for example, the backward modeling of algebraic matching that we use in cybersecurity. Now examples. So we can present, for example, the binary code of as the behavior algebra expression. We can scan binary code, convert it into the text presentation, or we disassemble it, and automatically present it as behavior algebra specification. It will be the system of behavior equations and the set of actions that present the semantic of every machine instruction. For example, here we did the experiments with the x86 Intel assembler. Behavior equation defined with the control flow, and afterward we can apply formal methods for the specification, especially detect the vulnerability on the level of the binary code. So the next slide shows the example how program written in C is translated into the behaviors. Here behavior equation represent the control flow program. It also can be presented as graph, and the action with the help and breadth postcondition represent the semantics of the program operator. This is done automatically, and the program presented in the language of behavior algebra can use formal methods located in the that are located in our algebraic server. The same is for hardware. We have also created the translation from the hardware design languages such as VHDL and System Verilog. This slide shows an example of how this is represented in the language of action and behavior. Having formal model of device, we can analyze different properties and find the different vulnerabilities or backdoors, as well as we can check the safety violation like race condition, buffer overflow, etc. So vulnerability patterns or the algebraic signature. Our algebraic approach has been applied for such cybersecurity task as vulnerability detection. We consider the vulnerability from the world database, CWE, vulnerability database and weaknesses of database. Known vulnerabilities of software system as well as attacks and their semantic can be represented in behavioral algebra. This slide shows the example of vulnerability, especially the stack damage vulnerability, which consists of writing information in an unauthorized area of the stack, which destroyed the execution of the program, and in the case of an intrusion, the control of the program is intercepted. This is represented for binary code or for code in machine instructions. So the vulnerability is the system of behavior equation that covers all possible scenarios leading to vulnerability. They are represented by a pattern that is a set of action. So it shows that some input from the information from outside, and then arbitrary behavior, and then the allocation of stack, then again the arbitrary behavior, and then the right outside the boundary of this stack. Such patterns are created manually according to semantics of vulnerabilities. So the vulnerability pattern is used in the algebraic matching algorithm to detect vulnerability. It worked as follows. So a binary code is an input which is disassembled and translated into algebra behavior. Algebraic matching, which uses algebraic patterns from a database containing vulnerabilities, works next. We unfold the behavior equations and match the scenario with vulnerability patterns. When the matching is triggered, a verdict and the counterexample are issued showing the path leading to the vulnerability and the inputs that would make the vulnerability is reachable. This configuration can be used before detection of attacks as well, in real time by matching the current behavior of system with patterns. We did such experiments, but work of algebraic matching symbolic algorithm is time consumed, and such delay in work of system can cause its non-efficiency. To resolve this issue, we decide to check the efficiency of neural networks approach. So we use the known data set for training of neural networks that consider the classifiers of attacks as well as the classifiers of anomaly behavior of the system. First experiments we provided for Internet of Things, where we trained deep learning neural network for detection of 9 attacks, including spoofing attack. We get some accuracy, but it was too low, less than 80%. There are known disadvantages of usage DNS. Perhaps different modification of NN are used. We are restricted of data set, and it's hard to predict which data set is sufficient for normal accuracy of detection. Especially it is actual for detection of anomaly in system work, where a huge number of false positives occur. Also, we face with the overfitting and the adversarial attacks. It's also the issue. And one of my postgraduate students did some experiments for increasing of accuracy, and some decisions have been proposed. One of them is augmented data set and using of the verification of DNN techniques. Okay. One of tasks was to identify the malicious behavior of botnets, which are the source of the deny of service attack. So an open data set containing traffic packets were used from which features were extracted. There were already data for training of deep learning neural network. To obtain the features, some traffic reconstruction application was designed, which made it possible to extract features correctly. The problem of the reliability of the network with respect to adversarial attack and attempts by hackers to bypass the classification also was considered in this problem. The problem for this, the most sensitive feature that affect the classification were determined. Next, an augmented data set was generated with one had such values of sensitive feature that were significantly different from the usual ones were considered, but from other candidates, the data had to be plausible enough so that the neural network did not classify this data as deviation. This raised the accuracy of neural network quite a bit, but there were still problems. There were also a study of the verification of neural networks. We cooperated with British University with the vehicle application vehicle. It was created for language models and for images, and for verification some perturbation of data in the data set was used, and classification based on SMT Solmer was investigated. In the task of detection of botnet, we created a separate program that worked with the Microsoft D3 solver. So you can see the condition of the successful verification. It used the concept of neighborhood of some points. So if we have some perturbation in the scope of the input data, so we have the fixed difference in the, we should classify correctly. So, but as I said, there were also the problems. So we tried to consider the construction, which we called the cognitive networks, and this term is used in several contexts, and these contexts they are quite different from each other. So we combine two components, algebraic component and AI, based on statistical experience of AI and ability of algebraic component to derive facts from knowledge. In general, their parallel work can be defined as the learning based on example and conclusion from knowledge and making decisions based on experience. Such approach is called in literature the neurosymbolic approach. And we have some experiment in the implementation of this approach. This is some kind of implementation of cognitive network. So we have a system to be protected. The system accepts some information from the external environment. The system can be a software system that accepts internal traffic, or system that accepts the data in the scope of some telecommunication protocol, especially satellite system. We store the model of the system in the behavior as the behavior algebra specifications. We understand that it is impossible to detect all system vulnerabilities in a finite amount of time by algebraic manner. Therefore, the model is both stored and checked continuously to search for known vulnerabilities using the algebraic matching algorithm. The result of finding of vulnerability is an exploit, that is input data that can lead to an attack. When we find a vulnerability in a system, we store all exploit in our database to block incoming stream in the future. It's some kind of constraint over their data, over the input data. As a front end, we have one or more DNN performing attack classification. The incoming stream is temporarily blocked in quarantine. The classification time is quite short, so the delays have almost no effect on the work efficiency, main classification of the DNN. If the DNN has not detected an attack, then the data is passed to the system. If the DNN has detected an attack, it is necessary to make sure that it is not a false positive. To do this, we check the exploit database, which contain constraints, and perform data matching with them. If an attack does not exist, then we block the data and signal an intrusion. If the attack is defined by DNN but not contained in the constraint, then we perform an algebraic modeling of the system and check whether the attack data will lead to some safety violation. If we have determined by algebraic modeling that this is an attack that has not been identified, that we enter it into the exploit database and other signaling intrusion. During modeling, we can retrain DNN with new attack cases by correction of the weights. So this is another method of combination of algebraic approach and AI. So we used this also was some experiment that we provided. We use the technology of incorporated constraint in a neural network. The technology was tested on the task of detecting attacks on satellite networks. We considered two open data sets and created the corresponding deep learning neural networks. As a part of the neural networks, the additional layer was added, which contains rule containing formalizing attack semantics. It's contained the constraint. Sometimes we incorporate it in the loss function, and sometimes and there's some kind of the filter. Incoming data is pre-validating during and avoid delays in the operation of the satellite network. In this case, the constraint can function as a filter that excluded the false positive. Constraint can be used for testing if the semantic of the attacks are presented in more details, and in the case of mismatching with the verdict of neural network, the weights of neural network can be adjusted. Now the option when the layer with the constraint work as a final in case of positive detection of in final, yes, the final layer to prevent the false positive. So we did the experiment with the traffic from satellite system. We consider the open sources, we consider the sources, the specific sources, and we also consider the example of attacks for for the hardware system, especially for integrated programming circuits, FPGA, and it is now used for it was deployed in the detection of backdoors and the detection of safety violation in the Kropivnitsky enterprise, which create the devices for nuclear energy. So the conclusion that neurosymbolic approach shows that we can avoid the false positive at least, but there is still a lot of program, and so we are moving forward in this direction, and I hope that we will create some combination. Well, for example, we use the combination of the anomaly DNN and the multi-classifier. So it can give it's our the last development. It can give a new results, and I think it will be much better accuracy and without losing the efficiency and its speed of detection. So I think that it's very perspective direction, and we continue work and cooperate with different university and private. Thank you for the attention.
Thank you. Questions, please. Questions.
Alexander, thank you. I have just one question. So you mentioned adversarial attacks. You mentioned like epsilon as a perturbation radius. What vector norm were you using? L0, L1, L2, what norm?
Sorry, last just this distortion was the last.
Yeah.
What
vector norm were you using like to evaluate vectors for discerning the attacks? Like Chebyshev?
Yes, we did. Yes, I understood. Yes, we use different one because it's just an experiment. It's just not a product. We have different the else.
More question? Thank you. So we complete our work successfully. Thank you all.